All right, well, good morning. We're going to continue on with our Chapter 2 discussion about chemistry. Specifically, where we're going to delve into today is the chemistry of one of these really interesting, but it's ubiquitous, right? It's everywhere. It's found everywhere, especially when you look at this picture right here. It's quite clearly what I'm going to be talking about over the next few minutes. If you look at our planet, we're 2/3, 70%, something like that, water. Even our cells are made up of mostly water. Water is an essential ingredient to life on this planet. It's an essential ingredient to life as we know it, to carbon-based life forms. So that's why sometimes when you read reports of astrobiologists getting very excited, or astronomers getting very excited about the presence of water on another planetary body, be it a moon of Saturn or one of the other exoplanets, because of the fact that if there's water there, of course, then perhaps, especially if we think about in our own solar system, then perhaps life as we know it has evolved. And think about when I'm saying life as we know it, what I'm really saying is a chemical aspect of it. Remember I said early on in the semester, I'm pretty sure when we were talking about carbon, that carbon is a central element to living things on this planet. And not just human living things, that's every living thing on this planet. And what I mean by it's an essential element, it is the foundational element that's used to make all the different life forms on the planet. It's one of these interesting things that we always talk about in biology, known as the unity and diversity of life. And the unity idea being that we're all carbon-based. Carbon is great for building structures. It's a great structural foundation for all these different molecules. We all have that in common, whether we're talking about prokaryotes or eukaryotes or any of the critters that we've talked about. We all have that in common. We all share DNA. We all share the same type of hereditary molecule on this planet. So that's the unity. And of course, the diversity is the fact that there are fungus and there are plants and there are animals and there are all kinds of protozoans and all kinds of prokaryotes out there, right? They're all very diverse. So that's what we mean by that. Another thing that ties into this unity of life is, again, water. Water is essential for life as we know it. Hence, the Earth has quite a bit of water on it, and the Earth has quite a bit of life. There are other things, of course, that are necessary for life other than water, like in our case, the right amount of sunlight and all that. But we're going to focus our attention on the chemistry here. Now, let me remind you once again about these water molecules and the uniqueness of a water molecule. Again, I love in biology or in science sometimes looking at a very common object or common item in a different way. And so we're looking at water in a different way. We've been looking at it all our life. We've swam in it, fished in it, all that sort of stuff. But remember, water molecules, when they bond together, when the atoms, the two hydrogens and the oxygens bond together, that oxygen does not share those electrons equally. Polar covalent bonds, right? So what that ends up happening is these molecules take on those positive negative ends, which and then those stick together, which we call hydrogen bonds. We talked about those previous, right? Now, those hydrogen bonds, they're very weak, easy to break, right? You just got to tip a pitcher of glass up, okay, that's enough. Then you've broken a hydrogen bond between the last water molecule that fell and the one that's still back in the pitcher, right? But they're extremely important, these hydrogen bonds. Very weak, but extremely important, not only in water molecules, but later on when we start talking about our hereditary molecule, hydrogen bonds play a key role in your hereditary molecule, your DNA molecule. So those, again, hydrogen bonds, extremely weak, but very effective. Now, in terms of water and the reason these hydrogen bonds are so important, chemists will say that many other compounds similar in chemical properties to water. Now, if you think, what do you mean chemical properties? Same molecular weights, all those things that make up a property of a molecule, same physical properties when it freezes, that kind of stuff. But they say if we look at molecules similar to water, and one doesn't cross my mind at this particular point, but I believe benzene is one of the things they looked at, if I remember right. Was the fact that at the temperatures we find on Earth, our distance to the sun, that water should not be a liquid, and it is mostly a liquid. I just showed you the picture on Earth. There's some solid water, there's ice, there's some gaseous water, water vapor, steam, all that stuff. But most of the water on Earth is liquid water, and the reason why that is because of these hydrogen bonds, you see. Without the hydrogen bonds that would attract these molecules together, those molecules would drift further and further and further apart. And when they get further apart, their density decreases, And if we think about what density in states of matter, when density decreases in a state of matter, it becomes a gas, doesn't it, right? Solids have the greatest density, usually. Liquids, medium, and gases have the least. And density is how much is crammed in an area. So those molecules are far apart, the density decreases, and the stuff becomes gas. But see, those hydrogen bonds, those very weak hydrogen bonds, allow those water molecules to just stick together, enough to keep them a liquid, enough to keep them close. Now, we all know you can heat up water and turn it into gas, and we'll talk about that in a second. But in the temperatures we find on Earth, the typical temperatures we find on Earth, right, those water molecules, those hydrogen bonds between them are just enough to keep it a liquid. So let's take a look at the properties of water. 5 listed here. 2 of them I've lumped together. So I kind of look at it overall as 4 properties of water. But you'll see what I mean when I combine the other 2 when I get to that. The ones that are combined with the box around them, right? The properties of water. All right. First property, water. Water molecules are cohesive, right? They stick together, right? I guess I should actually use the word they're cohesive and adhesive, right? Because they do both. Cohesion and adhesion have different definitions. Now, if you're worried about this table, seeing it again, I'm going to keep coming back to it as we change between the properties. So I want to stick with cohesion. Cohesion is when like molecules stick together. See the picture there? See where it's defining it? 2 water molecules stick together by cohesion. Water molecules can also stick to other things by adhesion, like the sides of the walls of the cells that conduct the liquid, the water up into the higher parts of the tree. You saw an example of that in class with the graduated cylinder, right? Remember when you looked at the graduated cylinder, the meniscus? That's because the adhesion between the glass and the water is greater than the cohesion of the water molecules, so it pulls the water up a little bit, right? So water molecules are cohesive or adhesive, again, depending on what they're sticking to, because of those hydrogen bonds. Now, if you're thinking, well, how does adhesion involve a hydrogen bond? Well, whatever makes the sides of those water-conducting cells that you see in that really cool electron microscope picture, whatever it's made of, many times the structure of those cell walls or sides of the cell there will also have sticky ends. And not sticky in terms of glue, right, but sticky in terms of atoms and electrons binding with each other. So water molecules can stick to the side of those water-conducting cells in a plant, same way it sticks to the side of the graduated cylinder, right? Very important for getting water up a tree. If we think about biologically, very important for these guys not falling through, right? Great pictures. You can float a needle very carefully, and a dime, by the way, on a surface of water. Because of surface tension, right, those critters, that water strider and that really cool spider up there, and that needle can float on the surface of the water. Now, you got to have just the right amount of spread of your weight out there on those legs, and that's why it's easier for these multi-legged critters to do that. But what they're doing, go back to my little picture here, is they're pushing on these hydrogen bonds. And these hydrogen bonds, I want you to kind of think of, for at least through the rest of this discussion, are kind of like springs. They spring back and forth. So when those little critters are pushing on those water molecules, they're stretching but not breaking. If they broke, they'd stick to the bottom, not breaking those hydrogen bonds. Isn't that neat? You can't do that. You weigh a little bit too much. Your density is a little bit too high, and you certainly don't have the body structure of these legs spread out real far to be able to do that. Now, you can float in salt water if you're thinking, well, that's different. That's because due to density. You're not floating due to surface tension. Okay, now I'm ready to talk about the other 2, which I've combined, and the reason I have is because the 2 properties are chemical excuse me, properties of the chemistry of water. Give me a second. For example, water has a property called high specific heat. Now, lots of things, items, liquids out there have a specific heat, okay? A specific heat, okay, let me switch back and forth between this one and the definition slide that I have, because I like to have it sitting in front of you as I say it, especially because so many times it just, it's easier to see it as well as to hear it. All right, so water absorbs heat from warmer air, releases stored heat to cooler air. Okay, all that's going to be talked about as we go through this idea that what we're doing here with water is we're moderating temperature. Don't make this more difficult than it is. This is what your water, your coolant in the engine of your car does. Right? That's why you have coolant in your car. That's why if you lose coolant in your car overheats. It's the water and then coolant, and then it goes to the radiator where it's cooled off again by the wind blowing through it as you drive. It goes back to the engine, right? So water can absorb a lot of heat, and the important thing about absorbing a lot of heat is water can absorb a lot of heat before it changes state. Once water becomes steam, it's of no use to you in the engine of your car. It's out, right? So you're done. You got to stop. It's got to stay a liquid to be effective. So those hydrogen bonds, those really slight hydrogen bonds, again, think of them as springs. As the environment warms up, those water molecules on those hydrogen bonds, those springs, start doing this. They start vibrating. They start vibrating. And what happens is the hotter it gets, the more they vibrate. But they remain a liquid. Now, you can eventually get them so hot that they vibrate, and they break apart and they become steam. They turn to a gas. But it takes a lot of energy to do that. Takes a lot of heat. You got to really heat them up a lot. That's what we mean by water can absorb and it can release a lot of heat with only slightly changing its temperature. It's a good moderator. All right, a couple definitions here, a couple little numbers. So let's go through this and just make sure we understand what we're talking about. Lots of things have a specific heat. Water happens to have high specific heat. Well, let's define that. Let's define specific heat. Now, if you had physics, you've probably seen this, but if not, it's very simple. It's going to be the amount of heat, and we can measure heat in calories. We can measure heat in something called joules, which isn't spelled like jewels on your, that you wear. Anyway, there are many ways to measure heat, and heat is energy, folks. Heat is energy, right? Same thing. There's many kinds of energy, and heat is one of them. So specific heat is how much heat it takes or must be lost for a gram of something to change temperature 1 degree Celsius. Okay, a gram of that substance. Lots of things have a specific heat, right? Other liquids have specific heat, low, high. Water has a defined specific heat, right? But specific heat just means anything that a gram of it that you can cause to change temperature by 1 degree. In the case of water, the energy measurement, the heat measurement that we're talking about is calories. So you see down below with the arrow, 1 calorie in water, 1 calorie of heat will change 1 gram of water 1 degree Celsius. So gaining a calorie will cause it to 1 degree Celsius. Losing a calorie will cause it every gram to lose 1 degree Celsius. That's how we define calorie, by the way, the things we talk about in food. That's the amount of heat that you need to raise the temperature of 1 gram of water 1 degree Celsius, okay? When you eat 500 calories for a Big Mac, actually those are kilocalories, by the way, but that's another story. It's just sort of an easier way to refer to them in the food industry as calories. But that 500 calories that you ate in that Big Mac represents the amount of heat it would need to raise, say, 500 grams of water 1 degree Celsius. Or you could raise 1 gram of water 500 degrees Celsius. Thank God it doesn't do it that way, though. It's a little bit warm, but that's what that Big Mac does for you. It raises 500 grams of water in your body by 1 degree Celsius. That's the amount of heat. Of course, most of that energy, I guess I should really qualify that, most of that energy is going into what it's supposed to go into, which is power your body. Heat is interesting. It's what we call wasted energy. It's unorganized energy. It's sometimes you've even heard it called dirty energy. It's energy that's hard to do work with. You can do work with it, but it's hard. Think about laying out on the beach and warming up. It'd be hard to think about doing work with it. Now, if you're going, wait a minute, what about photovoltaic cells, solar power? Yeah, there you go. Now you're getting how we're learning how to do that. But that's sunlight is much more than heat. Heat can be used to do things, but it's a difficult energy to use. You see what I mean? So at the very bottom is the bottom line chemically. Water resists changing state, temperature and state. It's hard to boil water, all right? It's hard to freeze water, okay? So what does that mean for us? Well, that kind of fits in with the next property, the high heat of vaporization. So once again, many substances have a heat of vaporization, all right, per quantity. Water happens to have a high one. So what that means basically, do you and I, is come back here to my water molecules. Springs are bouncing. It's getting warm. It's getting warmer. I'll come back to this in just a second. So in a human being, look at the guy down the left working hot. We all know what that's like here in Florida. We sweat a lot, right? So what's happening in this case by this heat of vaporization, that's a property of water, physics, chemistry, right? Living things take advantage of that, because what that means is when water and those bonds are bouncing back, it's absorbing heat, keeping you cool. Eventually, when the water does, the bonds do break and it becomes steam, it evaporates off your body. You sweat. That's what I'm talking about here. When that happens, water has a high heat of vaporization. In other words, water removes a lot of heat when it does that. Right? Heat of vaporization is the amount of heat 1 gram of liquid must absorb to be converted to gas. Water happens to be a gram of liquid that you need a lot of temperature to do that. So what happens is when it evaporates, we call something called heat transfer. You evaporating that liquid up the surface of your head or your body cools your surface quite a bit. Now, did the bouncing hydrogen bonds cool it? Yes, they did. They cooled it as much as they could until it got too warm and they started to turn to steam. You started to sweat. Now, here's the thing. That's good, this high heat of vaporization. But from a living perspective, you got to remember you don't have endless water unless you're drinking it. That's why it's always important to remember to remain hydrated in the summertime so that when you sweat, you have the water to sweat. Because here's what happens. Once that water turns to steam, it gives you a nice cool dose, right? It helps cool off. It's no longer available to help you cool off again because it's down in the air. You got to drink water. I read an interesting article about how Thompson's gazelles, that little critter in the middle, keep their brain cool especially in the heat of the day where they live in Africa, because lots of your body can get warm, but you don't want your brain to get too warm. Your brain's pretty sensitive to being too warm, and it starts making you do things like not spot predators or something. It's something you shouldn't do. So what they do to cool the blood that's going to the brain is it comes up from the heart. Now, down below, if you look, the little dash line, this is the artery. So arteries take blood away from the heart. And then the blood enters into this really weird thing. It looks like an interchange on a freeway. But essentially what that does is that works like the radiator in your car. And that cools the blood that's coming up from the body where it might have been warmed up by the sun or the animal running. But the way it cools the blood is also shunted or routed, if you will, into the nasal passages of these critters, big nasal passages. And they use it for smelling, of course, but all these arteries and veins that are in the nasal passages, as the air passes over them, it cools them off. Just like the air passing through the veins of the radiator of your car, right? Then that cool blood mixes with the warmer blood from the carotid artery in that little interchange, and the result is overall cooler blood for the brain. So the carotid artery is bringing up warm blood. Some of that blood's been diverted into the nose where it's been cooled off, and it's coming back and mixing again in that interchange, and overall it's mixing the warm and the cool water, or excuse me, blood, but enough to lower the temperature of the brain, just enough. Sometimes it's only a few degrees. Very important stuff, right? So this ability of water to absorb a lot of heat, all right, that bouncing on the bonds, that's important for us. And then, of course, like I said, once you bounce those springs enough, if you pull on strings hard enough, you can break them. Once you do that, you release a lot of heat. But with the caveat, from a living creature, you got to bring that water back in, right? Once you've done that last-ditch effort to remove heat, you've been bouncing on those springs. Because the bouncing springs, that's where the heat goes. It doesn't go into your body. It doesn't go into your vital organs. Well, it does, but the water in there is absorbing heat, not the mitochondria and the nucleus and those things we don't want to absorb the heat, and proteins and all that kind of stuff. All right? And then eventually they break, turn into steam, you lose a lot of water, but you got to replace that. Now, what's cool about this whole heat of vaporization is it explains how animals, critters, organisms stay cool or get rid of excess heat. But it also explains our climate, too. So I was stationed in San Diego in the military, and it is some of the most beautiful weather in the world. I mean, it's all year round about that temperature you see there, about 70. It's a gorgeous place to live. But this temperature profile that you see is 1 day. So while it'll be 72 just a mere 80 miles away in Palm Springs, and I've been there so I can attest to that, it'll be 106 degrees, right? 34-degree difference. Isn't that amazing? The reason why that happens the way it does is if you look out there where the Pacific Ocean on the West Coast, well, obviously on the West Coast, is cold, very cold. Used to go to the beach there a lot, but did not get in the water a lot. But notice the water is 68 degrees. All right, so that's colder than the springs are around here. Springs here are about 72 degrees, about San Diego temperature. Well, the reason why San Diego and Los Angeles and Santa Barbara can be nice and comfortable at 70, just, gosh, look at LA and Burbank, just maybe 20 miles away, the temperature could be 15 degrees hotter or even hotter out towards the east there, is because that nice, cool Pacific Ocean is moderating the temperature. See, these are temperatures during the day. So when the sun comes up in Palm Springs, it gets 106. That cool Pacific Ocean is sucking up that heat, just like it would cool you off if you jumped into it, sucking the heat from the air, keeping San Diego nice and warm. And then at night in many places, when the sun goes down and there's no more heat coming from the sun, the ocean will then release that heat and warm the air back up again. So at San Diego, it can get relatively cold at night, but that ocean does kind of mitigate that. It gets really cold at night in San Diego because there's very little water vapor. Water vapor traps heat, so you don't get a lot of that. If you want to look at a comparison of a planet similar to us without water, at least now, you can look at Mars. Without this ocean, without this water to be able to absorb and moderate the heat, you get a really wild temperature range during the day. Right? Minus 75 at night to 0, a nice balmy freezing during the day. And so as Elton John says, it's cold out there. It's not some place you want to raise your kids. Mars used to have an ocean, we think. It may still have a subterranean ocean of some type, but without its ocean, it's pretty much going to get warmed and cooled off by the sun. Right? There's no water there to regulate that. See what I mean? Temperature regulation, right? Let me go back to the chart again. Temperature regulation. So the idea that water molecules can absorb heat, good for living things. They also takes a lot before they turn into steam. At that time, they remove a lot of heat, but again, it's water unavailable to you, and so you got to replace it. So I remind you once again about this whole interplay between the chemistry, the physics, and the biology. All right, interplay, this whole thing. And so what we got here is a chemistry, physics, and living organisms that are using water for temperature moderation to keep that homeostasis balance that I've mentioned to you guys, I'm sure at least 100 times by now. Okay, the next one down, the lower density of ice. Let me show you a picture that probably won't confuse you, but maybe should. There we go. On the left-hand side is a nice glass full of ice, iced tea, obviously it looks like. And the ice, of course, is floating in the glass, and nothing about that looks unusual. Except for the fact that at the beginning, I alluded to the fact that water molecules are anything but really unusual. Because if you look on the right, and that is benzene. I think I said benzene is one of the molecules that are similar to water in properties. But notice what happens with benzene. That's liquid benzene and then frozen benzene at the bottom. Notice that in benzene, we get something that really, if you think about it, if we use deductive reasoning, right? If we can say typically solids sink in liquids. I know not always. We did the thing with wood in lab and it didn't sink and all that sort of stuff. But typically solids have greater density. Therefore, solids with greater density should sink in liquids with medium or less density. And there's no shock there. There's no surprise on your face. This actually makes perfect sense over here, doesn't it, right? Solids sink in liquids. I take a rock and I throw it into the water. It's a smiley face with my right hand, sorry. I don't expect it to float. But then again, we throw solid water into liquid water and it floats and nobody bats an eye at that. Nobody says, well, isn't that kind of weird? How does how does solid water float in liquid water when typically solids sink in liquids? Now, if you're thinking, well, it's density, and of course you're right. But you might not know exactly how hydrogen bonds contribute to that density. So let me show you a graphic that I found that's really kind of cool. On the left is liquid water, and the yellow dots are the hydrogen bonds. And in liquid water, those bonds are very springy, bouncing back and forth. But as water cools off, the springiness begins to subside, and they spring a little less, and they spring a little less. And when they spring a little less, on average, the molecules of water, of course, are closer together. They're not doing this, they're doing this. So they're closer together. Each of my hands is a water molecule, maybe like this, I don't know. Anyway, so as it gets colder and colder and colder, and actually water molecules get as close as they can possibly get when they're about 4 degrees Celsius, 3.98. Now think for just a second back to what we know about Celsius and that system. 0 is freezing. All right, so 4 degrees Celsius H2O is liquid. So water has got its greatest density when it's still a liquid. Now you know that, or you intuitively know that, because again, ice floats. But let's talk about where the hydrogen bonds fit in. As those water molecules cool from 4 to 0, 4 degrees, 3, 2, 1, 0, as water begins to freeze. I mean, 4 degrees is still pretty cold water. You wouldn't want to jump in that, that's for sure. Those hydrogen bonds, those springs get closer and closer together, and then as they cool off beyond 4 degrees, they actually begin to push the molecules apart and set them into a rigid crystal structure like you see on the right-hand side. As a matter of fact, Mother Nature is so anal that when she forms ice, the distance between water molecules is consistent. 4.48, that's an angstrom. Little tiny measurement. So those distances between those water molecules are 4.48 angstroms. So that forcing of the water molecules back out to that distance, because they're cooler, oh, they're frozen. So they go back out, causes the density to decrease, and therefore that's why ice floats in water, right? Good for us, right? Because we can obviously use it to our advantage, especially if we're a living critter that lives underneath the ice. It's nice that lakes freeze on the top and they don't freeze all the way through, so that in the summertime, sure. In the wintertime, no matter what the temperature gets outside, the ice actually provides an insulation. So the water below remains a liquid, so the shrimp can live in that liquid water, while up above the ice, my goodness, the temperature could get minus whatever, right? Really, really cold. Orange Grove folks in Florida do that. See down below? They know a freeze is coming, they'll put water on their crops, because what that does is that provides just a bit of insulation on the leaves. So if the leaf or the ice is 0 and the leaf is in contact with 0 degrees, that might be just enough to keep it alive in case, like, say, the air temperature drops to, say, -2. Remember, sometimes in life, it is just a degree or two that makes a difference. It's like global climate change when people argue, well, it's only changing a degree or two. That's really a big effect when you look at the huge overall effect on the planet, right? And then I think that's just a cool picture of the husky. I've always been fascinated by, like, canine behavior, and I just wonder what this animal must think walking on ice. You can see through it, but I can walk on it. If they can process that. All right, enough about ice floating and the good things for us, right? Let's go back to that chart. Water dissolves lots and lots and lots and lots of things. As a matter of fact, water is what we call a universal solvent, solubility, down at the bottom. Now, if you're saying, well, it doesn't dissolve oil, no, it doesn't dissolve oil. It only dissolves like. It only dissolves other, polar substances. And the reason why this happens, let's go back and take a look at a water molecule up close. If you're thinking, I bet you it's something to do with those hydrogen bonds again, you would be exactly right. Because if we take a look at the solubility, here's how it works. It's something that gets dissolved in something else is called a solute. So a solute, I always say, gets dissolved. The solvent does the dissolving, and that makes a solution. So saltwater solution, salt is the solute, water the solvent. And as I mentioned to you in lab the other day, when we were talking about how glucose forms up in a ring, that's because it's more stable that way in water. And living things in the world is an aqueous environment. An aqueous solution is where water is the solvent, right? Water doesn't have to be the solvent. Many other things are solvents, but if it's water, then it's aqueous, water. The reason why this is, once again, is back to those hydrogen bonds. That's why we call it the universal solvent. If we're thinking about a salt crystal over there on the right, the positive and negative ions of the salt crystal, Remember, when I talk stickiness here, I'm not talking about adhesive. I'm talking about magnetism kind of thing, right? So you notice the water molecules down below, the positive ends up by the hydrogens, the gray or white. They're attracted to the negative ions of chlorine and the opposite for the sodium. And what it essentially does is you get a lot more water molecules than you got sodium and chloride ions. So each one pulls with those slight hydrogen bonds, but through time, they eventually break it apart. That's what we call dissolving. That's what we call dissociating, right? Those ions are coming apart. And it forms what we call, you can see around there with the water, those hydration shells, right? Because what happens is the water actually just circles, or kind of like the circle in the wagons around each of those ions. But the end result is we see the stuff dissolve. Water is good at doing that to most everything. That's what we mean by a universal solvent, right? It dissolves most. There's probably some chemicals out there that may be, man-made, I'm sure, human-made. So not just men who do all that. Women sometimes make stuff in laboratories that we have problems with. But water also dissolves proteins, good for us because we need proteins for food. And how does it do that? Well, proteins have sticky parts on them. See in that little, what do you call it, inset picture? See how those water molecules, man, I'm telling you, anything that's sticky, they're good at tearing apart, ripping apart. Now, why is that good for us? Well, solubility is good because we're mostly water. Our cells are mostly water, and chemical reactions, when we're going to talk about enzymes and photosynthesis and all that, all those chemical reactions are floating in a cell in a pool of water, essentially. The cell is mostly water, and that water provides a chemical social lubricant, right? What I mean by that is that water, because it dissolves everything's floating around, provides a great soup for everything to mix. And the reason why things need to mix is because some things need to come together and do something, need to do some chemical reaction. And I'll come back to this when I get into enzymes and start talking about it, remind you of water's role in all this. But remember, water's good at dissolving lots of things, creating these soups, right? Okay, so those are the 4 properties of water for biological organisms. The fact that it's sticky, cohesion, adhesion. The fact that it moderates temperature. The thing about ice having a lower density. And the fact that water can dissolve most things. Again, all attributable to hydrogen bonds. All of them. Those slight little bonds that otherwise, just blows me away. Otherwise, we wouldn't be here talking about them. If water hadn't had that property. Okay, we've gone over this a couple of times just briefly, but I want to make sure we get the definitions correct. Hydrophobic is something like oils and waxes, fats. They don't dissolve in water. They have no affinity for water, whereas things like vinegar, bases, ammonia, hydrogen sulfide, that smelly egg gas, are dissolved in water, hydrophilic. It's the old adage that I learned in chemistry, like dissolves like. Hydrophilic dissolves hydrophilic, hydrophobic dissolves hydrophobic. Now, let me remind you, hydrophilic substances, if they dissolve in water, are like water, so they are polar. And on the other hand, if you're not, then you're the other one, right? You're non-polar. I'm not going to write polar, but you know what I mean. This is what I mean about oil and water really don't mix. Even though if you take, like the oil companies take those dispersants and disperse the oil that they spill all over the Gulf. What happens here is dispersants cause the little droplets of oil to get very, very small, but they still get surrounded by the water. You think, how's the water attract the oil? It's not. It's actually repelled by the oil. So you can make something by causing it to come together. You can also make something by pushing it away, right? Okay, so these little bubbles here even have oil in with the water all over them, but they're not mixing. They're not dissolving together. It's not hydration shells in the same way that you saw with the ions. Now, we're going to turn our attention in a few chapters to cell membranes, and we'll talk more about cell membranes and how they work and how they structure, but I do want to introduce you to one type of molecule that is neither or maybe both hydrophilic and hydrophobic. It's amphiphilic or amphiphile. These are molecules that are both hydrophilic and hydrophobic. Now, what I mean by that is you got to remember that molecules are a thing. They have a size. So what we mean by this is part of the molecule is attracted to water, part of the same molecule is repelled by water. The reason why there's a picture of Tide detergent up there is Tide is an amphiphilic molecule, the detergent. Most of the dirt in your clothes is oils and that kind of stuff. Most of the dirt you would get on your clothes and stains are non-polar, hydrophobic. So you throw them into a washing machine and you add water, what good is that? Water's not going to pull off the oils. It's not going to be attracted to it. It's going to be repelled. So the amphiphilic molecule bridges the gap. The hydrophobic part of the Tide attracts to the oil, the dirt, the stains. The hydrophilic part is attracted to the water, so when the water is drained away in the rinse cycle, boop, they all go together, right? The dirt is taken away. Now, the little molecule you see down below is a really simple model. That molecule has carbons and all kinds of other atoms in it. That one that I'm talking about, if you're going, what molecule? This thing right here. This is called a well, there it is, thank goodness. A phospholipid. A phospholipid, which we'll talk about more later on. A phospholipid, very important for cell membranes, but they are like that Tide molecule. They have a hydrophilic head, and they have hydrophobic tails. All right, so the part of the molecule is attracted to water, part of the molecule is repelled by it. Now, when I get into the membrane structure, I'll talk about how that gets resolved in a cell membrane. It's very important. These are molecules, not living things, but because of these properties, this amphiphilic property, again, we wouldn't be here. That's what makes up cell membranes. What do I got left? Okay. Before I forget, if you listen to this before the hurricane, make sure you look at LSCC's website for any information about classes being canceled other than that. I may post some announcements in Blackboard too. I guess that depends on whether you have electricity or not, but nonetheless. Let's talk about this thing called moles. You might have thought I meant the critter up above, but no. We have moles. We have moles and shrews. They're called shrews, small little moles. I'm not talking about those kind of moles. I'm actually talking about this interesting thing in chemistry called a mole. Now, it's not a chemistry class, so we're not going to spend a lot of time and a lot of mental energy talking about and working with moles, but you will see it if you go on to other biology classes, chemistry classes, and it is important to talk about. What is a mole? Something we define, just like a pound, a kilogram, meter. We defined it, right? We said this, remember the king? That's a pound, holds up a rock. We call this number, this definition of a mole, Avogadro's number, named after Avogadro, some physicist or scientist from, I don't remember. Anyway, here's what a mole is. A mole, in abbreviations for a mole, just like kilograms would be kg, MOL, little m, is 6.02 times 10 to the 23rd molecules of anything. Okay, 6.02 times 10 to the 23rd molecules. Big, big number. That's a mole. So if I have a mole, if I have 6.02 times 10 to the 23rd, so that's, move the decimal point, 23, 21 zeros after that number. I don't even know what number that is. I have what we call a mole. I have a mole of that material. Okay? If I have 6.02 times 10 to the 23rd oranges, yes, the fruit, I have a mole of oranges. If I have 6.02 times 10 to the 23rd Buicks, I have a mole of Buicks. You understand? The number. Now, how do we use that? Well, oftentimes in biology and chemistry, we want to calculate something known as the molecular mass of something. Oh gosh, what is this? Well, it's very, very simple. Right? Skip the arrow part for just a second. Let's go to the example. Let's go down here. Oh, my pen works. Thank you. Glucose. And that doesn't work. Glucose has the atomic structure, the empirical formula C6H12O6. That was that ring thing we looked at in class, and the linear we looked at in lab in class. Don't worry about chemical formulas for things. Of course, I wouldn't ask you to memorize those. Don't worry about atomic masses for those atoms. I would either give those to you or you could ask me those. I'm not worried about you memorizing those. I want you to know how to use them. All right, so I went and got the atomic masses of carbon, hydrogen, and oxygen and rounded them, just like we did in class. We're not worrying about the electrons too much here. Atomic mass of carbon is 12, hydrogen is 1, and oxygen is 16. Right? Remember, the atomic mass is the number of protons plus the number of neutrons, and electrons, but we don't really worry about it. All right, here's how you calculate a mole. It doesn't get any harder than this. You take the number of atoms of a particular mass and you multiply those two together. 6 carbon atoms, each weighs 12. You add that to each of the elements in the compound or in the molecule, glucose. There are 12 hydrogens, each weighs 1. And there are 6 oxygens each weigh 16. 6 times 12 plus 12 times 1 plus 6 times 16, 180. All right, what's that number? 180 grams. So I tell you, go get me a mole of glucose. All right, you calculate this out. You go into the lab. You withdraw 180 grams of glucose. It's in a bottle, a sugar, basically. You withdraw 180 grams. You put it on the scale. There's 180 grams. You say, there you go, Professor Clark. That's 1 mole. And I go, oh, well, then that is 6.02 times 10 to the 23rd molecules of glucose. That's 1 mole of glucose. 1 mole of glucose is 180 grams of glucose, and that 180 grams contains that many molecules. See how easy that is? CO2 then, we could do that one real easy. We got 1 carbon and 2 oxygens. Let me do that in my head real quick, but I believe that's 44. Yeah, 12 plus 32 is 44. So 44 grams of carbon dioxide, which is a gas, you wouldn't be able to do it that way. Well, you would. It still has a weight, is 1 mole and contains 6.02 times 10 to the 23rds. Don't make this more difficult than it is, right? That's all I really need you to know is how to calculate that. And I want you to know what a mole is. I don't care about the 6.02 really. I want you to be able to calculate how many grams is a mole, and then I want you to understand what the word molarity means. See, in abbreviation, it's a capital M. That's why I emphasize the mole as a lower M, M-O-L. A molarity is if you took 180 grams of glucose, or whatever the molecular mass is it for the substance, was it 44 for carbon dioxide, and you put it in 1 liter of water. So the standard is 1 liter of water. So if I take 180 grams of glucose and put it in a liter of water, I have a 1 molar, not like your teeth, a 1 molar, big M, solution of glucose. Okay? Don't confuse those two. All right. Let's, if we're able to get to the lab on Monday, then this would be the lab we'd be working with. It has to do with acids and bases. So let me explain to you what they are. I mean, we all have heard about them, but now we're going to go drill down a little bit, perhaps, to talk about what it is chemically that makes an acid, and a base, because they do have definitions. Not everything is an acid. Water's not an acid, right? Vinegar is an acid. Sulfuric is an acid. Things like oven cleaner are not. They're the other one. They're the bases. Chemically, when we talk about something that's an acid, it's very simple. Acids are things that donate protons, all right? And what I mean protons there, that's a hydrogen ion. See that? H plus. It's a charged atom, so we know it's an ion. This is a hydrogen ion. It can also be known as, aka, also known as, just a proton. Why is that? Because hydrogen has the atomic number 1. 1 proton, 1 electron. If it's positively charged, these are the words I'm going to use, and hopefully these make sense to you. If it's a positively charged ion, if it's a cation, it's been oxidized. Something's taken the electron away. Well, in the case of hydrogen, if you take away its 1 and only electron, what are you left with? You're left with a proton. Now, don't get confused and think that, for example, the sodium ion that I talked about earlier in covalent bonding, that's not just a proton, because sodium had more than 1 electron. It had 11. Only 1 was taken away. This is you taking away the 1 and only. I'm going to use those terms interchangeably this semester. Proton, hydrogen ion. Same thing, same thing. So when we mean dissociate, we mean, donate, we mean dissociate, We come together when we associate. So hydrogen and chlorine come together to make hydrochloric acid, right? And then they dissociate to form those 2 ions there. Now, hydrochloric, you've seen it only in the liquid form probably. It's not. It's something that's dissolved in liquid. When it dissolves in the liquid, it's the solute, so it dissolves. It dissociates. It comes apart. And when acids come apart, no matter what they are, they always give you protons. There and there. Matter of fact, there's a universal way of writing it. We say HX, if it's an acid, no matter what X is a variable, you always get a proton plus then whatever X is. That an acid is a proton donor, right? That's what it does in solutions. Okay, now on the other hand, a base does the opposite. It absorbs protons. Acids donate protons, bases absorb protons. I'll do the first one in a second, the sodium hydroxide, but let's go down here. Ammonia is a base. There's a proton there. The arrows back and forth indicate equilibrium in chemistry, but what we're saying here in terms of what we're using this for in biology, ammonia, yeah, sometimes if you eat too many proteins, you get ammonia. Anyway, ammonia takes in a proton, absorbs that proton, and makes what we call an ammonium ion, the thing on the right, the NH4+, okay? So it absorbed the proton. It's a base. Sodium hydroxide, the one above, does it a little bit differently. You got to focus on the fact that sodium hydroxide makes this thing. All bases of this type, because ammonia is another type, can be written with this kind of formula. XOH. It's the OH that's important for these types of bases, because what happens is that OH then combines with a proton absorbing it, right? Absorbing it, that's what bases do. And what's that make? It makes water. All right, so acids absorb protons, acids donate protons, bases absorb protons, and there's two ways of doing that. You can either absorb it directly, or you can absorb it through this intermediate reaction where something dissociates into what we call a hydroxyl. OH negative is known as a hydroxyl ion. Cool word because it's got a lot of Y's and X's and stuff. You can name your kid that. There we go. Hydroxyl. That's an X and a Y. Hydroxyl. Okay? All right, so then that leads to this. If you understand the idea that it's all about the proton concentration, then this makes perfect sense to you. Let's take a look at the scale first. Start in the middle where it's neutral. When we put brackets around things, you see those brackets? We're talking concentration of. So if I wanted to say concentration of CO2, I could use this shorthand right here. Just a concentration, how many? When the number of protons equals the number of hydroxyl ions, then you don't have net absorption or net release. It's an equilibrium, right? See in the picture to the left of the beaker, the number of red protons equals the number of black things that would absorb them. So they're in equality there. That's neutral. There's no pH. That's pure water. Actually, pure water in a vacuum. Because as I showed you, if you blow carbon dioxide into water, you make it acidic, and carbon dioxide from the air can get into the water and cause it to be slightly acidic, so that should be pure water in a vacuum. All right, what's this whole proton thing? Let's go up the scale first. Let's go up toward the acid side. When the pH is less than 7, all the way into 0, we're in the acid side. And the further you get away from 7, the stronger the acid becomes. Take a look at where it says increasingly acidic, the thing written on the side. Notice what the bracket is doing. Proton concentration is greater than hydroxyl. So the things that would absorb protons, hydroxyls, are in short supply while there's lots of protons. So overall, you're going to have a lot of protons in the solution. And the more you have, the stronger you are as an acid. Battery acid has lots of protons. Your stomach juice, gastric acid, has a good amount of protons. Urine, saliva, not as many, but still enough to be considered an acid. If you go to the other side, where you're absorbing protons, see basic? Hydroxyl ions are greater than the protons, so you're going to get more absorbing occurring. Those are bases, and the more that absorb, the stronger they are. Oven cleaner is a very strong base. Milk of magnesia, well, seawater is probably better, is just slightly basic. So it is about the hydrogen ion concentration. As a matter of fact, over on the right, and not to blow your mind with this math, it's not really much to it. If you look at how we calculate pH, what it is you take the hydrogen ion concentration, right? And then you take the log of that, little thing on your calculator called the log, and then you take the opposite of it, the negative symbol, then you're going to get the hydrogen, you're going to get the pH. So look down below. We want to know what the pH of something that has a hydrogen concentration of 10 to the minus 7. Now, if you're not real familiar with scientific notation, 10 to the minus 7 is going to be 6 zeros. Yes, 6 zeros to the left of 1. So it's 0.6 of these. Why does my pen work and then stop? Maybe the battery's going dead. 6 of these. 1. Yep. So that's the hydrogen ion concept. Really small number, right? So we take 10 to the minus 7 in the parentheses. We take the log of that. If you didn't calculate, you get the number minus 7. Jump to the next step. And then you take the opposite, and the answer is 7. All right, now make this very simple. If I give you a hydrogen ion concentration of 10 to the minus 11, how do you figure out the pH? Well, you could easily plug 10 to the minus 11, take the log, do all that stuff. But here's what I tell people. It's that number right there. That's your answer. pH of that is 11. pH of something with 10 to the minus 2 is 2. Okay. Now, in your body, so here's the chemistry and here's the biology link to that. In your body, you have a need to balance acidity and pH, or basicity, or alkalinity is the word for it. In other words, you want to keep things in equilibrium. You want to maintain homeostasis. This whole idea of acids and bases and what they do to each other, if you mix an acid and a base together, what happens is they neutralize one another. They become what we call a salt in water. They become an ionic compound in a water. But they're no longer acids or bases, so they blank each other out. So your body's going to take advantage of being able to do that to stabilize pH, and it's going to do it with things called buffers. Buffers are things that do what buffers do. They slow down the changes, or they stabilize the pH, so you keep homeostasis. So in this picture, start on the far right-hand side, because this is what you're familiar with. Water and carbon dioxide make an acid, don't they? We did it in class. We exhaled into a flask carbon dioxide, and we made phenol red turn yellow, and we said that means it's an acid, right? And there's carbon dioxide in your blood. I'm sure you know that. There's oxygen in your blood. There's carbon dioxide in your blood. It's the stuff you're getting rid of. Some of that carbon dioxide mixes with the water that's in your blood and everywhere and forms an acid known as carbonic acid. Now, that carbonic acid is a buffer. The reason why we say it's a very weak acid. It's not going to cause erosion of your blood vessels or anything. It's supposed to be there. But here's why it's a buffer. And these are the arrows that are pointing to the left. And I added some annotations to it to help out. If your blood becomes too basic, now you got to think about what I mean by that. Too basic means very few hydrogen ions. Remember, more hydrogen ions, more protons, you're an acid. Very few protons, you get into the side where you're base. So if your blood it has a shortage of protons, in other words, it's becoming too basic, carbonic acid will dissociate. It'll go this way. And what it does is it creates this bicarbonate ion, but it creates this. That's a proton. So if your blood's too basic, then it releases protons to bring it back towards acidity. Now, if it's the other way around and you got too many of these, then the equation, see, goes the other way. And those are being absorbed. Either way, whether it's releasing protons, carbonic acid, or absorbing them, it's doing that in response to the environment around them. So if your blood becomes too acidic for some other reason, there's too many protons, then it'll start absorbing it. If your blood goes the opposite, becomes too basic, it starts releasing those protons very gently, keeping everything nice and balanced. Buffers are also used in chemistry lab to maintain pH. If you had some reason to be studying, say, the shape of a protein, which we'll talk about, pH is very important, you might want to stabilize the shape of that protein, so you would want to stabilize the pH. Those of you that maybe take aspirin, but it bothers your stomach, aspirin is salicylic acid. So buffered aspirin has a little bit of a substance in there that absorbs that acidity, so you don't have the problem. All right, the next few slides are going to get us ready for the next chapter. Next few slides involve a type of chemistry known as organic chemistry. If you go on in biology, you'll actually take 2 semesters of organic chemistry after you take regular chemistry. Organic chemistry is specific because it involves the study of, you think, well, that's pretty simple, although organic chemistry is anything but simple, carbon and hydrogen, things we call hydrocarbons. Things that contain carbon and hydrogen, they may contain other things, right, other elements, but they're usually a lot of carbons and hydrogens. Like, for example, glucose is an organic. It's got oxygen, but it's C6H12O6. Methane, CH4, that's organic. Remember I told you that glucose can wrap itself up in a ring form, and again, the idea is it's a little shorthand. That's a carbon if it's not written. Up above is like those molecular models you did in lab, right? The carbon right here, that's there. That would be the oxygen, nitrogen, and then they're not the same color, but these two would be the hydrogens. Now, if you look at the elemental material on the right, lignin, this is real cool. Lignin is found in trees. It's a very durable substance. Matter of fact, it's one of the most durable substances on the planet. It's one of the most durable substances. What I mean is it doesn't break down very easy. Trees make it, but there's only a few protozoans and fungi, and I think some bacteria that can break it down. Now, why is that so important to break it down? Well, everything's got to be decomposed and recycled in our environment, right? If you look at lignin, look how big that molecule with all those rings. There's lots of carbons in there. And carbon is that essential nutrient in our environment. We need to recycle it. When things die, they need to release the carbon back into the environment so other things can use them. Now, what is it about carbon? Well, go back and look in the upper right. Carbon's atomic number, 6. 6 protons, right? 6 electrons. So how many in the valence shell? 2 in the first, 4 in the next. So carbon is looking to make 4 bonds. You notice in that model that I pointed out, there are 4 bonds. 1, 2, 3, 4. I'm actually drawing, but the pen isn't. There we go. 2, 3, 4. Now, I like to think of carbon as reminding me of Tinker Toys. I don't know if people play with Tinker Toys anymore, but specifically this part of the Tinker Toy. And, of course, the one in the middle even more so. It's a very simple wooden disc, but it's got a hole drilled in the middle. It's got a hole drilled on the side. It's got lots of holes. With those in the sticks, with Tinker Toys, you can make anything. You make a bridge. You can make a giraffe. You can make an airplane. You can make what's this little girl that looks like a guitar. Tinker Toys are wonderful because they're only limited by your imagination. However you put those together, I think of carbon as being that little dowel, that little round thing of the Tinker Toy. Because it's so versatile, carbon is, because that toy is so versatile, you can make anything with carbon. Again, that's why carbon, unity and diversity of life, right? The idea that we're all carbon-based, but there's so many life forms. What's it so great about carbon? Carbon can accessorize. You can do lots of things with carbon, right? Like, for example, when carbon hooks together in a ball and stick model, that makes a structure. If you have 2 carbons together in ethane, now, if you put a double bond between them, right, like you see in ethene, then you change things. It's all about shape and structure. So up above, we have what's called a tetrahedral shape, right? Ethane is sort of like a double tetrahedral. And ethylene is now planar. What we mean by that is when there's a double bond between carbons, that plane cannot bend. It's rigid, right? It's flat. Double bonds, like you see, cannot rotate. So the atoms on either side are locked in place. They can't twist. They're locked into place. Actually, I go back, they bend a little bit, but they cannot twist around. So the one on the left, the one on the right, they can't flip on that double bond. It's like having 2 axles between a wheel. It's not going to work. You can't have 2 axles. You just have one. Now, why is that important? Shape, folks. It's all about shape with organic molecules, right? We can do things like, for example, have short ones and long ones and put them in a chain. We can change the double bond. We can form them in rings like you see up above, different rings. Those are all different names, so they look very similar, but they're not. Cyclopentane, cyclohexane, there's benzene. Pyridine, 1-butene, 2-butene, the number because of where the double bond is. Butane or isobutane or methylpropane, they're branched. What diversity, folks? That's what I'm getting at here. Look at all the things you can do because carbon's got all them places. You can make a giraffe. You can make a plane. What you have? A guitar. You can make anything out of carbon. We are carbon-based life form. Everything on Earth, all this diversity. We get diversity in just the simpleness of how many we put together. We get diversity by creating isomers. Now, we've seen the word or the root iso before. Iso means same. And in this case, mer refers to molecule. What we mean by the same molecule is in these columns, those molecules have the same formulas. Like up above, pentane is C5H12. 2-methylbutane is the same thing. That's what we mean by an isomer. Same chemical formula, but in structural isomers, they're arranged, the carbons are differently. Pentane, they're in a straight one. 2-methylbutane, they're arranged in a T form. Different shapes, different molecules, different properties. Diversity, diversity. Here's the double bond thing again. You can have isomers based on which side the X is. There's no element X, but we're assuming it's the same thing. So if the X is on the same side, we call it cis. Remember, double bonds can't rotate. The X's are on the opposite side. We call it trans. As a matter of fact, sometimes if you're looking through the names of some organic molecules, you might actually see that little tiny cis in front of the name. Cis, you know, something or other, something or other, something or other. That means it's that particular isomer versus the trans. All right, so those are different. Down below, the hand, what's that all about? We're talking about enantiomers. We're talking about things that are mirror images of one another. Right? Your hands are mirror images. Those molecules are mirror images. We sometimes give them different letters, like to represent the left-hand one versus the right-hand one. It's not really left and right, but you might think that L isomer is left, D isomer, nah, it doesn't work that way. But the L isomer is one mirror image, the D isomer is the other one. Same chemical formula, very different in the way they work. Give you some examples here. Ibuprofen, right? The one that for headaches and stuff. Only the in this case they call it S and an R, but only the right-hand one works. Albuterol, for those of you who might have asthma or bronchial, it opens up your bronchial passages. Only the, excuse me, I said ibuprofen, the one on the right. It's only, the only effective one is the S1, the effective enantiomer. And then albuterol, the R is the only one that's effective. In Parkinson's disease, a molecule called DOPA, there's the long name for it, only the L version, the one on the left, is effective against Parkinson's. So you see, the only difference between those two is which glove you have, the left or the right. So there's a lot of diversity there, right? There's a lot of importance to get the shape right, which we'll talk, you know, as we start talking about proteins and enzymes anyway. Okay? Now, another way that we can diversify these molecules, what we hang off of them. What do you mean by that? Well, these things that we built in class. You remember? This is now you know what the X is. It's the rest of the organic molecule, like ethanol, right? Make sure you know all your functional groups. I'm not going to spend a lot of time on this because you should know those, but those functional groups hanging off those carbon atoms give them certain properties. And sometimes just a little tiny change in a couple of functional groups. Sometimes we can get diversity from just barely moving something like this. We all know the difference between a male and a female lion, I hope, right? Well, estradiol is the female sex hormone, and testosterone is the male, as I'm sure you guys are aware. Look at the difference between those two. Now, the things that are in orange, those are rings of carbon, so don't let that confuse you. But you'll notice the difference between testosterone and estradiol is those two things that are in blue in testosterone. The methyl group, CH3, and this is a ketone, right? The methyl group disappears, and the ketone gets turned to a hydroxyl. That makes one the male hormone, and you become male, and it makes one the female hormone, and you're a female, right? Little tiny difference. Now, there are other differences in molecules between them, but in one of the major sex hormones between the two, all you've done is change two of the functional groups, and you got different molecules with different properties, right? Pretty impressive. All right, I want to move on now into chapter 3. So let me see if I got those files loaded properly and they're ready to go. I think they are. Right there. There we go. All right, now chapter 3. Oops, sorry. What happened there? Let me do that. Chapter 3 is the last chapter in this group before you take an exam on it. But chapter 3 is where we start to make that connection even more so between molecules, chemistry, and how chemistry works, and living organisms. So we're going to be talking in chapter 3 about big molecules, like the one you see in the picture. This is a big protein. I'll talk a little more about what all the little squiggly and different colors mean, but that is important. This is a protein, and I'm going to say it once, I'm going to say it a million times. The shape of a protein is crucial. It's so important. Proteins that aren't shaped right don't work right. So you look at this protein and you go, it's kind of a blob or glob shape. You're right. Matter of fact, proteins are sometimes called that, aren't they? Globular proteins. Okay, do some terminology. In order to make a big molecule, a macromolecule, you got to start with smaller ones. You got to start with monomers. Mono meaning one. So this is, think about this as being a brick in a brick wall, right? The monomers are the bricks, and then the polymers, the word down below, poly meaning many, would be the wall of bricks. Okay, so monomers plus monomers make polymers down below. So monomer number 1 plus monomer number 2, and the monomers could be the same, or they could be different. But we're going to link those together, a bunch of them, until we create a mini molecule thing called a polymer, okay? So in your body, in what goes on in terms of metabolic reactions, in your body, there is a balance that occurs between monomers being connected together to make polymers and polymers being torn down to make monomers. Monomers are coming together to make polymers because that's how you build cell structure, replace old cells, replace skin tissue, damage, that sort of stuff, or grow. Polymers, because one of the things that you can do when you take a big molecule and break it down, like for example, starch. Starch is a big polymer of glucose monomers, right? So glucose is the monomer, and you link a bunch of those together and you make starch. When you break apart those starch molecules, you get those little glucose molecules, and those are little nuggets of energy. Your cell loves glucose, man. I tell you, glucose goes into your cell, into the mitochondria, and you turn that into energy. So it's energy release, right? All right, so chemistry behind this. I told you the other day, if you're looking at a functional group in class on an exam and you draw a blank as to which one it is, guess hydroxyl. And the reason why I say that is organic molecules, for them, always have an OH or a hydroxyl group hanging off them somewhere. It's a very common one. So where am I starting here? I've got a polymer that's 3 monomers long, and we're looking at how do we link the fourth, right? Very simple process. The hydrogen in the blue falls off of the longer polymer, the one with 3, and the OH falls off the unlinked. So we do a little alphabet soup again. H plus OH is H2O, isn't it? So what we say in this process is water was created, or between those polymer and the monomers, water was lost. So that's why we call it dehydration synthesis or dehydration reaction. Now, this isn't dehydration in the bad sense, right? This isn't you're losing water. This is dehydration in the actual chemical sense. Water was lost from those two, right, to create that water. Or another word for it I sometimes see might be a little easier is condensation reaction or condensation synthesis. Condensation is the creation of water. But the synthesis is important because what happens after that, and there's some enzymes involved that we'll talk about later, obviously it's not just with water, is they link together. Okay, so that's how we're going to go from monomer to monomer to monomer to another monomer to make these big polymers. The reverse, simple. The reverse happens when you want to break them down. You use water to split. Hydro and lysis is to split. Think about those terms so you don't confuse those two, right? Dehydration, reaction or synthesis or condensation, hydrolysis, water splits. The hydrogen from the water goes back onto the other side or goes onto that side of the shorter polymer, and the OH goes back to goes to the unlinked monomer. They have to be the same one. So I'm going to say those words hydrolysis and dehydration synthesis or condensation synthesis a million times. So make sure you become very familiar with those. Here's some examples. There's 2 glucose monomers up there being linked together to make something called maltose, and there's the water that was made. And then hydrolysis, we're going to take the maltose and split it in half using water. There's the OH, there's the H, and those are split. All right, I'm done talking about the overall idea about how organic molecules come together and split apart. I now want to move and discuss the different types of organic molecules, what we call classes or types. There's 4 of them we'll go through. We won't get through all of them today. We'll get through, I think, maybe the carbohydrates today. I believe so. Carbohydrates are a class of organic molecules that are used for, I like to think of it as medium to short-term energy. Right? Fats are long-term energy. I always kind of use a bank account sort of analogy. Carbohydrates would be like, say, the money in your pocket or your checking account, whereas your lipids, your fats, would be your savings account, right? Carbohydrates are going to be used, again, for energy, either long-term or short-term. The name, it's wonderful, tells us what's in there. The 3 basic elements in all carbohydrates are carbo, hydrogen, and then if you've had chemistry, you might have learned that when you put ATE at the end of the name of a compound, it implies there's oxygen. All carbohydrates have carbon and hydrogen and oxygen, and they're usually put together in a very set ratio. This is a general equation for a carbohydrate. So glucose is C6H12. It's always a 1-to-1 ratio is what I'm trying to get at. Now, glucose is only one kind of monomer. There are a variety of kinds. This list is not necessarily exhaustive of all the monomers, but just give you an example. And then another list of some of the polymers of various sizes. Notice the OSE ending right there. Things that end in OSE are very oftentimes carbohydrates. So that's just sort of a little hint. Starch is an exception, except starch's real name or technical name is amylose. Y. Hard to make a Y with your right hand. And then chitin. In science, CH, we're tempted to say ch like in chair, but it's actually a K. And chitin is another one that kind of goes against the grain with the OSE ending. But that's typically glucose, fructose, galactose, ribose, deoxyribose, which you might be thinking, isn't that DNA? No, that's only part of it. That's the sugar part. Among sugars, we also kind of break down their names to give you a little more specificity. For example, glucose and fructose and galactose, yes, they're all monomers. But if we're talking about carbohydrate monomers, we like to add the root saccharide. So glucose and fructose are monosaccharides, right? Monomers could be with the other groups, like lipids that we're going to talk about later on, but a monosaccharide is only a sugar. If they're polymers, then we can actually break it down by size. Disaccharide like maltose is 2 monomers. Oligosaccharides are medium-sized proteins, or I'm sorry, medium-sized molecules, 3 to 7 monomers, typically 3 to 10, 3 to somewhere in there. And anything greater than 7 is considered a polysaccharide usually. So starch would be a polysaccharide. So there we go. What we made up above was lag is getting me. Disaccharide. That was a disaccharide. Maltose is a disaccharide. Functional groups, right? Definitely important that you know functional groups. We can break, for the most part, monomers of carbohydrate down into aldehyde sugars or ketone sugars. The name should be obvious to you as to why they are called aldehyde and ketone sugars. If not, please come see me. You should be able to recognize those functional groups. So once again, to remind you, glucose likes to wrap itself up in a circle when it's an aqueous environment. This little picture on the right is just a shorthand version of that. Right? So we're going to simplify what glucose looks like. So let's look at a dehydration synthesis in glucose. There's 2 glucoses come together, water is made, and there's the disaccharide maltose. Or it doesn't have to be the same monomer. Glucose and fructose could come together and make the table sugar sucrose, another disaccharide. If we link a bunch of monosaccharides together of starch, we make something, of glucose, we make starch. But now here's where it becomes interesting. Back to that diversity thing again. Notice there are 2 types of glucose up above, alpha and beta. Notice the difference between them. Remark on how, or be surprised at how little difference there is. It's really only the OH on the number 1. This is actually the number 1 carbon. That's what that number means there. It's like a roadmap for organic chemists. So at the number 1 carbon, the OH is facing down. At the number in beta, the number 1 carbon, the OH is facing up. That's the only difference. All right. Starch is made up of nothing but alpha glucoses. So 1 alpha glucose after another, all put together by dehydration synthesis. So all the OHs are on one side. Cellulose, which is very similar to starch, all right, is a linkage of beta glucoses, but not only a different glucose, but they're flipped. Notice, this one is right side up. This one is upside down. Right side up, upside down. So they're alternating. Now, what does that do? Well, again, that different glucose, that slight difference allows plants. We don't use cellulose, right? We can't even digest cellulose. We can digest starch, that's the stuff potatoes are in, but we can't digest cellulose. It's roughage, goes in our body, comes out the same way. Cows can digest it because they have a bacteria that actually can break that bond, but we can't break that bond between here. We can do it in starch, but we can't do it without some bacterial helpers like cows do when it comes to cellulose. Now, what does cellulose do because of those OHs being on opposite sides? It's sticky. So take a look at the next picture. There we go. Start from the bottom. Okay, there's starch. All right. Starch is either just a simple chain like amylose. It might be branched a little. Glycogen is the way we store sugar. When you eat starch, you break those apart. Some of those you use for energy. The rest you stick back together. And glycogen, which is in your liver, that would be the money in your pocket. Okay, in my bank analogy. So you might think of starch as being, say, money in your checking account. Glycogen is money you're going to spend right away. You're going to use your glycogen energy first. Now, it's similar to starch. It's a little different, right, because it's animals. Plants store glucose as starch. We store it as glycogen. But plants also use the other type of glucose, right, the beta glucose, and flip it over so that when you get a long chain, look down below, when you get a long chain of microfibrils next to each other, guess what? They stick together. And what that does is it forms a very rigid structure that if we look at the cell wall of a plant, we see these fibers laid down in sort of like a fiberglass. Plants have cell walls. Animal cells do not. Cell walls help plants stand up against gravity. Right? Plants don't have a skeleton like we do. So plants use these microfibrils, this sugar, cellulose, it is a sugar, stretched out across the cell wall in a hatch pattern like you would if you're making fiberglass to give that cell wall some rigidity and some shape. Cool, huh? Now, I'll finish up one more slide talking about chitin, another little change. We take a glucose monomer and we add this group down below, and we make something called chitin. That's a chitin monomer. And we link those together to make chitin polymers. Chitin is interesting. Chitin is a very rigid structure. Now, it is a sugar, so it's kind of like cellulose. It's kind of like the non-plant version. Where do we find chitin? Exoskeleton of insects. You see that cicada as he's molting. What he leaves behind is an exoskeleton. There are skeletons on the outside, so it's exo, of chitin. Insects in general have exoskeleton. The wings of a bee are made of chitin. The exoskeleton of our buddy the roach there, the palmetto bug, right? Tell all the tourists that it's palmetto bug. It's really a roach. That's chitin. Next time you step on a roach and hear that crunching sound, you're breaking the bonds between those chitin polymers and breaking that molecule apart. It's like ripping those threads apart in the cellulose. I'll give you one last thing to think about, or maybe not to think about. This is a mushroom. Mushrooms also have chitin. Only animals and mushrooms have chitin. Plants do not. My Bio 2 class, I'll talk more about that, but that says something interesting about the relationship between us, plants, and fungus. In a very broad sense, it insinuates that human beings, or it suggests that human beings are closely related to fungi than they are to plants, which you may not have known that. Okay, I think that's time. That's the end of that lecture. We'll pick up with lipids next time when we get together. Please pay attention to any notices on LSC about classes, either from me or from the school when it comes to anything to do with the hurricane. And be safe. I will see you next week, hopefully Monday. But as I said, make sure you check the website.